Hey guys, how's it going? Today we're going to make a Pokemon machine learning model that tries to predict what a Pokemon's speed should be given its other stats like health, attack, defense, and so on. So we're going to do this in 6 easy steps. 1 is load the dataset. We're going to get that from Kaggle. 2 is select the features. We're going to do all this in pandas. Split into partitions, train, val, and test. We'll talk about that soon, but basically you want your dataset into one where you train, one where you use that for evaluating which is the best model, and then you leave that test set to see how good your model is after you've picked a final model. 4 is pre-process the inputs. So for each of the models, you have to do some sort of scaling function, which we'll talk about. 5 is pick the best model based off of that validation set, like we said. And 6 is evaluate the chosen model. Okay, so first off is load the dataset. How do we do that? Well, this is the only thing I'm going to copy and paste in because it's really just this annoying thing. To read it out, it's exclamation mkdir, so that's make directory tilde slash dot kaggle. So it's making a folder in the home directory called .kaggle. We do a cp, so a copy kaggle.json into that folder we made, .kaggle slash. We change the modifications on that file. What file? Okay, kaggle.json. We do have to upload this file called kaggle.json, which is from Kaggle. You can get this API token if you go to your account. I'm just looking for it right now. Here it is, kaggle.json. If you upload that, or if you go to Kaggle, you say generate API token, it'll download this kaggle.json API file to you. And if you don't have a Kaggle account already, you'll have to make that. Or you can also go to, I'll leave the link in this description, which is you can just download the CSV. You actually have to extract it and then upload that instead of the kaggle.json. But this is how I'm doing it. And then we'll do Kaggle datasets download the Pokemon dataset and unzip Pokemon.zip. Okay, so that loads, at least it downloads the dataset. Inflating says Pokemon.csv. So we have Pokemon.csv here, and we will load that with pandas. Okay, so pandas is an excellent library with in Python for data manipulation. If you haven't seen it before, import pandas as PD. We'll get original data frame. So when I type df, that means data frame, which is the main pandas object. Original df is equal to pd.readcsv. So it's a CSV. We're reading that. We pass in the path, which is just Pokemon.csv. Sorry about that. There we go. And we can just output the variable original df. Okay. So here's our data set. We have the names of Pokemon. You can see it goes up to 800, which is Volcanion. I think that's the end of Gen 6, I believe. So we have types. All Pokemon have at least one type, and some of them have two, and some of them don't have a second one at all. We have a total stat, but that's just a sum of all of these stats, which is not super helpful to us. So we have health, attack, defense, special attack, special defense, and speed. We also have which generation they're from. So as we can see, it goes up to Gen 6 or Pokemon X and Y. And we have whether they're a legendary or not. We are not going to use all of this information. And so that's why we are going to, down here, select features or which variables we want to use here. So I'm going to make this new data frame, which is basically a subset of the other one. Modified df, that's equal to original df. And then you just pass here in a list like this, which columns you want in the order that you want to see them. So we're going to get HP and attack, and we're going to get defense. And then I'm just going to make a new line here for readability, but it's not actually doing anything. Special attack, it's written like that. And special defense, it's also written like that. And finally, we're putting speed last, and that's for convenience sake for when we go to make a model that uses this, and that to try and predict, clearly I didn't type defense there, to try and predict the speed. Okay, so it's easiest if that column that we're trying to predict is either the first or the last column. Modified df, if I type .head, that just shows the first 5 rows. And we can see here it's the columns that we want. This is going to be, or these 1, 2, 3, 4, 5 columns. These are what we're going to be using for the input, which the machine learning model is going to try and use these to try and predict what that speed is. Okay, now we want to split into 3 partitions: train, val, and test. We can actually do this just in pandas. Some of you may be familiar with a scikit-learn function, and we will see scikit-learn shortly, but you don't actually have to do that. We can do shuffle df. So we're just shuffling the rows of the data frame. As you can see here, this is in order of like it's Bulbasaur, then Ivysaur, then Venusaur. But we want to shuffle the rows of the data set, and we'll see why very shortly. It'll be for doing this. So shuffle df is equal to modified df dot sample. So that previous one, sample, where the fraction is 1, which means we don't lose any data. We're just moving them around. Shuffled df dot head is that same data frame, except now you can see the rows are shuffled around. That is very useful because then we can just do this, where we do train df. So the train data frame is equal to shuffled df sub up until 500. So that means the data frame for training is going to be the first 500 rows of this. And then we can get the validation data frame, which is the one we'll be using to try and predict or try and figure out what is the best machine learning model to take. Val df is equal to shuffled df sub 500 to 600. And test df is equal to shuffled df from 600 till the end. Okay, so why did I pick these numbers? Basically, this makes training most of the data. It makes it the first 500 out of 800 rows. So that's the first 5 out of 8. And then it takes 500 to 600. Actually, we'll do 500 to 650 so that these are the same size. So 500 to 650 means that val is the next 150 after that. And then test df is the last 150. So that the splits are, as you can see here, length of train df, length of val df, and length of test df. It's 500, 150, and 150. Okay, so we have it into data frames now, except now we need to split it individually into inputs and outputs. So we can call this a matrix, the input matrices, because they are going to be, like this is really just a big matrix itself, except the input matrix is going to be just like 1, 2, 3, 4, 5 columns, and then whatever rows it is. So it's 500 for the train, it's going to be 150 for the val, and 150 for the test. And then the outputs, they are going to just be the speeds. So we don't really call those matrices, we call those vectors. Okay, so we need to get our input matrices and our output vectors for train, test, and val. We can do this with xtrain, and ytrain is equal to train df dot to numpy. So we're converting this to numpy. Generally, when we feed into machine learning models, we use something like numpy. So train df dot to numpy, and then we can take this where we say, I want all of the rows of that, but I only want up until the last column. -1 is the last column, so I say up until the last column. Now I'm just going to copy this piece because it's only going to be slight modifications to get exactly what we want every time. So now for the Y train, it's exactly the same here, still train, except it's not up until the last column. It is really just the last column. So this is everything but the last column, and this is just the last column itself. If I now copy this whole line here, it will be extremely similar for getting it for the validation. So x val, and that will be y val, and this will be from the val df, and this will also be from the val df. That's the only changes we have to make. And I'm going to copy this again. Actually could have kept the same one, but we're going to now change val to test over here. So this will be test, this will be test, this will be test, and finally this will be test. And then what I like to do is always output the shapes of these numpy arrays. And so xtrain, actually I'll put this in brackets so it shows which pairs we have. So xtrain.shape, and then ytrain.shape, and then comma, we can do xval.shape and yval.shape, and then we can do xtest.shape and ytest.shape. So that outputs, the shape is just the arrangement of the numbers that it has in there. So xtrain has 500 rows and then 5 columns. Its corresponding outputs are just 500 rows because they are only one column. It is just speed. This is the same, so 150 and 5, and then 150 for val, and then 155 and 150 for the test. Now what we can do is something called preprocessing. It's also often called scaling. And so what we do is we just kind of applying some transformation to the generally just the input variables, although there may be times you'd want to do it for the output variables. But something like divide all of the values by some certain number, like maybe the maximum value, or maybe we do something called a standardization. Today we're just going to look at something called the min-max scalar. So we'll do from Scikit-Learn.preprocessing, we will import the min-max scalar, and we get a scalar, this object, which is an instantiation of this thing, min-max scalar. And then we fit this with xtrain. It's important that we're just fitting it with the train. And then now that we've fit that, it means it learned some number to divide by and some numbers to subtract by, basically. I don't want to go through the exact operation it did, but basically you can now consider a scalar as this fixed function where it's not something that's going to be learning anything. It's just applying the exact same transformation to everything, and we want to apply the exact same transformation to xtrain to make xtrain scaled, to xval to get xval scaled, and xtest to get xtest scaled. And so these each are just going to be scalar.transform each of its parents, basically. So scalar.transform xtrain, scalar.transform xval, and scalar.transform xtest. So now what we'll do, these are the things that we actually care about, and I don't know why it's giving, yeah, no, this is right, I don't know why it's complaining at me. So now what we're going to do is just make a data frame, so pd.dataframe of xtrain scaled, so that we can make a histogram of that very easily with .hist. And so what this does is it shows for each of its columns, which are, we lost the column names, the lovely column names of like health, attack, speed, or sorry, not speed. This will be everything but speed. It'll be health, attack, defense, special defense, or I forget which ones they are. Sorry. But basically, we can see that all of these values are now between 0 and 1. And this is generally an important first step for creating machine learning models, is to do this pre-processing thing, where all the values, all of the columns are on this similar range of data. Every single thing here is between 0 and 1 or so, which is very good for many machine learning models, especially deep learning models really care about this. Now what we want to do is pick the best model, considering the lowest validation error. So what does that mean? We will see very shortly. First, what we want to do is always create something called a baseline model, which is really just, a baseline just means something for comparison base, where it's not necessarily a terrible model, but it's something that you should definitely be able to improve upon. And if you don't improve upon it, that means your model is not very good. So we're going to calculate the average speed, which is simply ytrain.mean. So that is one number. It is, if we were to look at it, that number is simply 66. Okay, so 66.7 is the average speed. Well, the most simple model always is just calculate the average and then use that as the prediction every single time, disregarding the input. So what I mean by that is if I get something called from Scikit-Learn.metrics, we want to import the mean absolute error, which is simply it's something that's going to produce a number that is greater than 0 because it is absolute value. And it's a mean absolute error, meaning we get the average of the absolute errors or distances between the predicted and the actual. Okay, so if I feed in mean absolute error on yval, okay, why am I doing val? That's for validation. And that, remember, we are trying to pick the best model based off of the lowest validation error. This will make even more sense shortly after we train a different model. So we want to compare the observed y validation values to our predictions. And our predictions are simply going to be the list of the average speed times the length of yval. That way it matches in length to yval, and every single prediction is just going to be the average speed. We will compare each of those to the y validation and calculate an overall mean absolute error, which is, for this, 24.74. So that's our baseline metric. It means by on average we are off by about 25 speed, which is actually not that terrible, but we can definitely do better than that. Now the simplest model we can create is the linear regression model. So we'll do from sklearn, sklearn.linear model. We'll import a linear regression. And then we can make a linear model and train it with linear regression, bracket, bracket. We fit this with passing it xtrain and ytrain, so it's always training on that training set of information. And then we calculate its error, same thing, compared to yval. So yval, and then linear model dot predict with xval. Okay, so we get the predictions corresponding to the input matrix from the validation set, and those we compare those predictions to the outputs for the validation step. Very, very similar to above, except this average speed model, that had nothing to do with actually training a model, aside from just learning what the average of the training set was. Now we can compare these two models, and we see here this got 20.69 compared to 24.74. This linear regression model is on average much better than the average model, which is as expected. Now we'll make a more complicated model, which is going to be a random forest. So we will do from sklearn dot, it is under ensemble, it's an ensemble model. We'll import a random forest regressor. Okay, not classifier, but regressor, and we will make a random forest, not random forest equal to the random forest regressor, and we'll just leave it as the default variables for now. We can change number of estimators as well as the max depth, but we're just going to leave that for this tutorial, and we'll do .fit with, again, xtrain and ytrain. It's always going to look like that, and it'll also always look just like this for looking at the error of it, the mean absolute error of yval, but then this model, random forest.predict with xval, to get 20.32. Okay, so we actually got 20.382. Okay, so we got a little bit of a better model on the random forest, but is it better enough to actually use a random forest? Because it's nice to use a linear regression because it's such a simple model and it is very, very explainable. So I'm not sure if the trade-off of the slight accuracy on this random forest is enough to steer away from the linear model, but it's really up to you. You can also make a gradient boosting model, and you can do a k-nearest neighbors model. There's a bunch of different scikit-learn models you might want to use, but we're just going to leave with these two for now, and then do two neural networks. So we are going to make a shoveled neural network, which is really going to be pretty much the same thing that a linear regression does, except it's going to do it from a deep learning approach, and then after that we'll do a bigger neural network. So we'll do from TensorFlow.keras import layers. So I don't know where that went. Import layers. So a neural network is made out of layers. We will use these. And from TensorFlow.keras.models, we will import the sequential model. Okay, so it's a sequential. We're going to say in order, we're going to build up these layers. We need an optimizer. So from TensorFlow.keras.optimizers, generally we take the atom optimizer. And now we'll make up our model, which is going to be, as I said, very, very simple for this first one. We'll just call this model model 1, I guess. Model 1 is equal to a sequential model, where first we take an input. So we do a layers.input, and we specify it's actually just going to be, we're putting 5 comma, we're just giving the shape of the input, which is simply 5 numbers. It's health, attack, defense, special attack, special defense. Yeah, I almost got lost there. That's what they are. And then we will convert this to a dense, which is just going to, it just really means a number. Layers.dense with 1. And by default, the activation is going to be linear, meaning this is simply just going to be a number from anywhere from negative infinity to infinity. But don't worry, it's fine with it just being positive values. It'll figure out that it wants to be positive for sure. So then we need to do something called compile the model. So we'll do model1.compile. where the loss is MSE, the mean squared error. That is a different error function than the mean absolute error. It's a little bit less interpretable. This is more useful to us because it's saying, okay, we're off on average by about 20.4. This one would say this squared error is off by whatever it would be. It's a little less interpretable, but it's better for machine learning models to optimize this. We're going to be using this optimizer to optimize it. And so we pass it the MSE. We will make the optimizer. So to try and minimize that mean squared error, we want low error. That's going to be Adam with a learning rate equal to 0.01. Don't worry too much about that, but basically I'm specifying some sort of learning rate value. It's how quickly or how slow the machine learning model will learn. We'll do metrics is equal to the list of, we can pass the string of just mean absolute error, and TensorFlow Keras will recognize that. Actually, it will if I do this. And it'll output this when it goes through many epochs, and we'll just see visually what that means in a moment. Model1.fit, where we pass the input is going to be xtrain. The output is going to be ytrain. We need to pass the validation set here. So validation data is equal to xval and yval. And epochs, which means how many runs through the data set do we want to do. First, I just want to visualize one with you. So we'll do one epoch. That's clearly should be a t there. Okay, so it very quickly did this. It spit out this loss function, this loss value, which is actually going to be the mean squared error on the training set. We have the mean absolute error on the training set, which is 41. Val loss, which is the mean squared error on the validation set. And the mean absolute error on the validation set is 27. If we now let this run for, say, 100 epochs, it is going to keep going down. And if it lets me scroll over here, there we go. We can see at, well, it already did it, but I'll just let it finish for a second so that we can look at the very, very top. So at epoch 1, it was a little higher here. So it was the val mean absolute error, which is what we're really monitoring. We're trying to get this down. It goes from 31 to 29 to 28 to 27 to 26. It goes down and down and down, and it doesn't seem to really get any better than about 22 or the high 21s. So this model looks like it's just a little bit worse than this linear regression model, which is a little bit weird because it's very similar to a linear regression. The way that we constructed the network, it's actually just 5 inputs, converting it to 1, which is really what a linear regression is doing. But Scikit-Learn, I guess its algorithm's a little bit better at doing this than the deep learning one, and so it's a little bit better. And you'll actually see that as a common theme. That'll happen very commonly. Let's try something else, which is the same thing. And I'm going to copy paste this. I copy this model, and then we will do a model 2. So model 2, 2, 2. We'll keep everything the same, but I want to just add some complexity to make this a more complicated neural network. So we'll try a dense, which converts it to 32, and then it converts it to 32 again. And if we compare these two models, if up here, we can actually do something called model1.summary. We can see here there's just 6 parameters. That's 6 numbers that we have to learn, which is actually, again, the same as what a linear regression would have to learn. It would have to learn 1 for each of the variables that's coming in, and it's going to learn one other variable called the bias or intercept term for linear regression. And here, if we make a more complicated model 2 here, I'll just let it do its 100 epochs, and then we can do the summary afterwards. And here it again gets to maybe the high 20s now. So it did a little bit better than the shallow neural network, we'll call it, basically a simple neural network. So did it do any better than the other models? High 20s? Well, these are mid 20s, low 20s. So it did about the same, actually. It wasn't really too far off. So which machine learning model would we take? Actually, sorry, before we do that, I do want to say the summary. So if I do model2.summary, This is trying to learn 1,281 values. So instead of learning 6 values, it's trying to learn 1,281. So you can probably guess that we don't really want that if the linear regression model itself is about just as good. We want to pick the linear regression if it's not too much worse than the other models, because it's a lot more interpretable and it's just very quick to run. A lot of people know what it is. It has a lot of benefits. So for this, we decide that linear regression is the best model. Now what we do is evaluate the chosen model. And so we have this linear regression model. We called it linear model. And what I mean by evaluate is we left that test set until the very end. We have not touched it at all. We kept training off of the training data. We kept seeing how good it was on the validation set. But now what we're going to do is finally see, okay, how good is this model? After we picked between all of the models above, we picked a model. Here's a test set where we can say, if we get the mean absolute error on y test, and then we do, it would be linear model dot predict on the x test. If we get that value, it says again, just to finally confirm for us that it's about 20.27 that we'll be off by with our linear model, which is pretty good. That's actually a pretty good model to try and predict the speed. So I hope this was fun. I hope it was a nice beginner project, that it's nice and interesting. I love Pokemon so much. I hope to make more Pokemon projects and all of them in the future. And subscribe if you're not, for sure. And I will see you next time, guys.